Hey, welcome back to Math with Patrick. Today is December 21st, and we're solving problem 355 from the Daily Epsilon calendar. We need to find the number of 8-digit binary numbers where no two consecutive digits are 1. So binary is just a number system where we're only allowed to use two digits, 0 and 1. If it is calling it an 8-digit number, I do think it's necessary that we put a 1 in our whatever place value this is. Just because, for example, thinking of base 10 numbers, I wouldn't call 90 a 3-digit number. That doesn't make sense. I don't think a leading 0 makes sense for a 3-digit number. I believe the problem will agree with me today that we do need this leading 1. And if we have no two consecutive ones, that does force this to be a 0 immediately. And then after that, it gets a little bit harder. I think for starters, we probably could just count them up. We only have so many spots left. We know they must be zeros or ones. And then counting up 21 things might not be that bad. So let's try it out. We could try to think what would happen if we added no more zeros no more ones. So that would mean that we're only putting zeros in the rest of our binary string. And that's totally fine. We can just fill out a whole bunch of zeros. That would be the value, let's see, this is the 1, 2, 4, 8, 16's place, the 32's place, 64. Okay, so this number right here, if I filled in all these as zeros, would be the number 128 in base 10. And this is a valid 8-digit binary number, and we have exactly one thing we can do when we add no more ones. We could think about what happens when we put one more 1 in here, and we could put it in any position we want. None of those spots will cause a double up on our ones, so any one of these 6 spots is valid, so we have 6 more potential numbers here. This 2 more case is going to be a little bit harder, so I'm actually going to skip to the 3 more case. We could put the 1 here, and then that would necessitate the soonest one possible would be here, and then finally the soonest one possible would be here. So this is kind of like the first number that I'm thinking of creating with no consecutive ones. I do have a little bit of leeway here, right? This 1 could have been in either of these spots. So I'll put a 2 right here to just represent both of these numbers that I'm thinking about. Then we could change it up, and maybe we could move this first one over a spot. So it would be right here, which would require the next one to be here, and then the next one to be here. And I don't see any wiggle room out of this, so there's one more option here. Maybe I missed one. I think there's one more option. Let me put this 1 back there. There we go. So we could have had a 1 at the end, and then there is also this option to stick this 1 in either of these spots. And I'm not going to put another 2 here. I think I would be double counting if I put a 2, because I already accounted for this scenario right here in this 2. So moving this 1 over here does give me a new setup. Overall, I have 4 different options to stick 4 ones in a binary 8-digit number that has no consecutive ones. Okay, let's put 2 more ones in here. I could either stick it here or here. And then for this one right here, I do have a lot of options of where it could go. Looks like there's 4 different spots that this last one could go, so I'll put a 4 here. Then we could move this one up a little bit, and maybe it goes here. The other one now has 3 options for where it could go. And then we can just run this process down until we can't place any more ones. So I could place 1 here, then we have 2 options, and then finally I could just place them here and here. And that gives me 1 more option. And I believe I counted everything because I considered all the cases where this digit is a 1, and then there is no case where this digit is a 1, and then I check that one and it's also a 1, because then we would have 2 ones in a row. So just by counting, I think I found them all. This should be the number 21. We do have 10 options here. Great, okay, nice. And then 6 plus 4 is another 10. And then finally, when we add on that first one, we do get 21. Now, there is a way to think about this with, I think, the Fibonacci sequence. We could think of it as like a recurrence relation, and I'm actually curious to try it out real quick. So we know that we must start with 0, 1, and then we have an option, or we have many options for how to fill out the rest of our 6 digits. And as long as this 6-digit string is a valid string, then we should count them all. And by valid, I just mean that it's made up of zeros and ones, and it doesn't have 2 consecutive ones. So for this one, we could think of our first digit, and it could be 0 or 1. That's basically it. And then if we think of our 2-digit options, we could either stack 2 zeros, we could do 0, 1, we could do 1, 0. This is fine because we have a 0 before it, but we can't do 1, 1 because then we double up our ones. And there's a recurrence relation we can do here. If we think about our 1-digit options, we could tack on a 0, 1 to any of them because, well, 0, 1 is totally allowed. And then regardless of whether I have a 0 at the end or a 1 at the end, the 0, 1 will make sure I'm not doubling up on any ones. So both of these could turn into new options. It's 0, 0, 1 or 1, 0, 1. And then for my 2-digit strings, I could be allowed to put a 0 at the end, although maybe I'm not going to be allowed to put just a 1 at the end because I would be doubling up on one of them. So here, if I just tack on a 0 at the end of these, I should also be creating brand new, totally valid binary strings that don't have consecutive ones. And this 000 is okay to put here. I don't need this leading 1 anymore because I already kind of guaranteed it. And this is this recurrence relationship that will help us fill out all the other possibilities. Now that we know all of our possible 3-digit strings, we can now play the same game. We can take our strings from maybe 2 steps back and then tack on a 0, 1. So we have 0, 0, 0, 1. We have 0, 1, 0, 1, and then 1, 0, 0, 1. And then we can take any of our strings 1 step back and tack on a 0. 0, 0, 1, 0, 1, 0, 1, 0, all zeros, 0, 1, 0, 0, and then what looks like 1000, but this would be the number 8 in binary. And if you do a quick glance, I don't think I am doubling up on anything. And I know I'm not actually, because in my first string, I'm ending with a 1, and then my bottom string, I'm ending with a 0. So I'm never going to create the same number out of this step. And this is actually just the Fibonacci sequence. We're just adding the totals of the previous 2 to get to the next one. The 2 possible 1-digit strings and the 3 possible 2-digit strings add together to get the number 5. That counts how many we had here. Then we can use the 3 and the 5 to count up to 8. And we do have 8 possible strings here. That means that we can use 5 and 8 to get 13 possible 5-digit strings. And then finally, 8 plus 13 gives 21. And this is the total number of 6-digit binary strings that we can write that don't have 1, 1 somewhere in it. And then we can insert that 6-digit binary string somewhere here, and then we'll get a valid number for our problem today. So I think that's about it. We can just count the numbers, or we can use this Fibonacci sequence to figure out that there are exactly 21 numbers of this type, and we're all done. So thank you for watching, and I'll see you tomorrow. Bye.